Let me increase the voice. It's max now. Yeah. So hello everyone. Today I'm going to discuss two Leetcode problems. Uh, these both of these problems are interrelated. So first of all, I'm trying to build some algorithm for problem one. Then I will try to optimize this for problem two. So without wasting much time, let's start with the problem one. So this problem is Leetcode 3006. Find beautiful indices in a given array 1. Okay. So we are given a zero based index string S, string A, string B, and an integer K. Okay. And index I is said to be beautiful if and only if uh, substring. It's a substring of length of string A. Okay. If S from I to I plus AI mod A minus 1 is A. Okay. These are some constraints and these are conditions. Basically, question is saying uh, I is said to be a beautiful integer if and only if the substring starting from index I uh, in string S going till mod A minus 1, basically mod A size. So this I can be beautiful index if and only if this substring is equals to A, and for this index there must be at least one j such that s of j till mod b minus 1 is equals to b. Okay, so basically yeah, I can be beautiful if and only if there is at least one j existing for particular I, where si till s of a I plus mod a minus 1 is a, and sj up till s of j plus mod b minus 1 is b. Okay, and there is also another condition on I and j. It is saying that I minus j mod should be less than equal to k. Okay, so first of all, let's analyze the situation. If this is a string s, I can take, first of all, let's say the length of string s be n, length of string a should be m1, and length of string b be m2. Okay, so I can take m1 size substring from any index, and I can take m2 size substring from any index of string s. If these strings are respectively equal to string A and string B, and this condition is holding, then that particular I is beautiful index. And what we need to return is, we need to return a sorted order of beautiful indices from smallest to largest. Basically, we are asked to store beautiful indices in sorted manner. Okay, so I can be at left, j can be at right, j can be at left, and I can be at right. So no matter what uh, are their mutual ordering, both of these conditions should be satisfied. First condition is this, that we have substring starting from ith index of size a should be equals to string a, and substring starting from sj of size b should be equals to string b, and this condition should hold in between both these indices I and j. And for each I, we need to find at least, we need to have at least one j to make this I beautiful. Okay, so if we have this mathematical relation between I and j, that is mod I minus mod j less than equal to k, if I just simplify this relation, I can find that j should be greater than equal to I minus k and less than equal to I plus k, right? So let's try to build some algorithm for this problem. Let's say first of all, I'm storing all these i's such that uh, substring starting from I of length m1 is equivalent to string a. I'm storing all these i's in a vector. Similarly, I am storing all these particular j's in another vector such that s of j up till j plus m2 minus 1, basically m2 size substring, is equal to b. I'm storing all these j's also. After storing both of these j's, to store particular beautiful indices, what I need to check is, we need to have at least one j such that this condition holds, right? So let's say if I am able to find at least one j, the first j which is greater than or equal to I minus k, and it is also holding this condition, that means that particular I is a beautiful index, right? So I can store these i's in big O of n cross m1 and these j's in big O of n cross m2. How I can do this? If let's say I am doing something like this. This is a string. I am iterating. I is iterating from 0 up till n minus 1, and for each I am taking a substring of length m1 or m2. I am checking whether this substring of length m1 or m2 is equivalent to a or b, and respectively I am storing I and j. As I am taking length m1 for each index, that's why this iteration should be of big O of n cross m1, and in this case it should be of uh, big O of n cross m2, right? So after the storing part, what I need to check is if there is a j which is satisfying this condition or not. For this, I need to find first I. Let's say I am finding first I which is greater than or equal to I minus k, and which is also satisfying this condition. Then in that case, that I is beautiful, right? So let's I am I am checking for each I. Basically, for each I am finding first j which is greater than or equal to I minus k, and checking if this is satisfying this condition. Then I am storing the I. This is what I need to do, and this operation will cost me how much? If I do this operation smartly, I can do this in big O of m1 log m2, right? By use of binary search. Yeah. So this is what I need to do in this problem. So let's examine overall time complexity for first iteration part where I am storing I, it is n cross m1, and where I am storing j, it is n cross m2, and the third step where for each I am checking whether j exists or not. It will be big O of m1 log m2. So if I put the values of n, m1 and m2, it will be almost big O of 10 to the power 6, which will be a valid solution, right? So let's go to the coding part of this problem firstly. Yeah. So we have to return a vector of it. Let's say I am storing n as s dot length. M1 is equals to a dot length. 2 is equals to b dot length, and I have to store the valid i's and valid j's. Let's say I am storing valid i's in array vector arr and j in brr. Okay, so let's say I am iterating from I equals to 0 till the range is given to me, right? So I is less than equals to n minus m1 I plus plus. If I have s dot substring starting from index I of length m1, if it is equal to a, that means that particular I is a valid index. So let's store that index in a vector arr, right? Let's do the similar thing for j index also. Index j is equals to 0 to j is going from 0 to n minus m2 j plus plus. If s dot sub str, basically I'm considering substring starting from index j of size m2. If this string substring is equals to b, store this store all these j's inside this vector brr. After storing this, I am done with my step 1 and step 2. So let's go to step 3. In step 3, what I was doing is, first of all, let's create a answer vector. So now let's iterate on each index, valid index I present in ARR, and let's try to find whether J exists for that I or not. So for that binary search part, as we all know that if I have a sorted array, like increasing sorted array A, and I need to calculate first element which is greater than or equal to x, this is basically the definition of lower bound. So I can directly use lower bound STL for that. If you don't want to use lower bound, you can implement binary search on your own also. But here I am using lower bound STL, lower bound uh, brr.begin to brr.end, and taking lower bound on. I am taking lower bound on this I minus k, because j should be greater than or equal to I minus k. Yeah. First, let's check whether this uh, particular j exists or not. If it is not equals to brr.end, that means that at least one j exists for that particular condition. That means that particular I was a beautiful index. So let's store that in answer. Okay, I have stored that in answer I, and yeah. After that, let's return answer. Let's try sample test cases now. They're working. Let's submit the code. Giving me wrong answer at this test case. Why? Yeah, I have to check this condition also. That particular j should be less than equals to I plus k. I have to check this condition also. Yeah, I guess now this error should be resolved. J is basically dereferencing that iterator. Correct now. Let's submit the code. Got accepted. So this was the problem one. This was part one of this problem. So let's go to the part two. In part 2, if you can see, the problem statement is again you are given zero based strings s, a, b, and integer k, and index I is beautiful if and only if this condition holds and there is a substring starting from index I of length m1 which is equals to a, and there is a substring starting from index j of m2 which is b, and again this condition is still same. Then what's the change in this problem? Yeah, there is slight change in constraints. In previous problem, we have constraints like n was up till 10 to the power 5, k was up till 10 to the power 5, but m1 and m2 was up till 10. But in this case, we have n is approaching to 10 to the power 5, m1 approaching to 10 to the power 5, and m2 is again approaching to 10 to the power 5. Let's say if I try the previous algorithm in this problem also, what will be the time complexity? As the previous algorithm was of big of n times m, it will be up till 10 to the 5, and multiplied by 10 to the 5, it will go up till 10 to the 10, which will definitely give me TLE. So I have to optimize that algorithm. I can't use it directly. So let's check the previous algorithm and check where there is a scope of optimization. If you can see that in this step, both of these steps, what we are actually doing, we are basically checking whether the string A is present in string S or not. And if it is present, I am basically storing all these particular indexes from which it is starting in string S. And again, I am doing the same job in with string B also. Yeah, it's basically string matching. And if you know, we can do string matching in n plus m time complexity also using string matching algorithm. Yeah, I'm talking about KMP algorithm. So let's say if I use KMP algorithm, KMP algorithm. So after using KMP algorithm, the step one will be of big O of n plus m, basically big O of n plus m1. Step two will be of time complexity big O of n plus m2, and step three will be again same big O of time complexity of big O of m1 log m2. And if I check the overall time complexity, it would be big O of n plus m. On rough note, I can say it's big O of 5 times 10 plus 10 to the power 5 plus 5 times 10 to the power 5. It's almost 10 to the power 6. This will be a valid solution. The basic slide change which I did in this algorithm is I just changed this step 1 and step 2 implementation. I just implement I will just implement both of these steps using KMP algorithm. In part of this problem, first let's try the previous algorithm also in this problem, part 2. Sample test cases are passing. Let's submit the code. VTLE. Let's try. It's giving me MLE at test case 216. Okay, so let's now change the code. First of all, let's implement the KMP algorithm. For KMP algorithm, first we need to implement the pi function or LPS, basically the largest prefix which is suffix. So uh, let me form a function. Let me create a function first. KMP. Right. In this function, I need a string s, string pattern, which I need to find in the particular string s. Okay. So firstly, what I need to have is I need to calculate the LPIs, that is the pi vector. So first of all, let's create a string total, which is s plus hash plus pattern, right? And I just store the length of string s. This complete string in TTL n is equals to TTL dot length, and store the length of pattern in string in integer m. Yeah. So after doing this, let's create a LPS vector or pi vector of length n, which is initialized with 0. Let's evaluate the pi vector for other indexes also. J is equals to pi of I minus 1. Okay, so let's first check whether j is greater than 0 and if the particular si is not matching with sj. So in this particular case, what I need to do is update j with pi of j minus 1. And if after coming out of this loop, or if there is no loop, just check whether si is equals to sj. If this is the case, increment j and update ii with j. Just not return. Just after this step, I have my pi vector. So let's compute a vector answer. Store, which will help me to store matching indices. Right. Okay. So let's iterate in this particular pi vector from I equals to m plus 1. Uh, should be pattern plus hash plus string. Yeah. Up till m minus 1 m and this m plus 1. Yeah. Iterate m plus 1. If the pi value of that particular index is equals to m, then store. I am using zero based indexing here, so store I minus 2 2m. Yeah, yeah, and just return the answer vector. You are not able to understand the implementation of this KMP algorithm, just go to CP algorithm website and refer this KMP algorithm from there. So or you can use this KMP algorithm as black box also, as your wish. So I have implemented that KMP algorithm, and now what I am going to store is I am storing all these matching indices I, which are matching string A inside string S in this vector. So KMP, let's give it S was the string and pattern is A, and vector BRR KMP. Yeah. Now we have stored. We are done with our step 1 and step 2. Let's go to the step 3 part. Let's create answer vector. Similar solution. Just iterate over all these i's inside ARR. Check whether particular j exists or not. So auto it is equals to, again I am using lower bound. PRR dot begin going to PRR dot end, and I am checking this lower bound over I minus k. If this iterator not equals to BRR dot end, that means that particular j exists. And also I have to check whether this j, that is the reference it, is less than equal to I plus k or not. If this is the case, that means that particular I was beautiful index. So let's push this I inside answer vector and turn the answer vector. Let's try to run the sample cases. Here is a runtime error here. So basically, this was the problem. I was using S instead of TTL, but the final string was TTL, the total string. So yeah, this was the error. So the sample test cases are running. Let's submit the code. Yeah, it got accepted. So this was the this were both of these problems, problem one and problem two. I guess both of these problems were interesting string problems. So that's all for today. So thanks for watching. Bye.